All right, here. Okay, so welcome back, you guys, online, and we'll get started here with Chapter 1 here, and I've called up the textbook to Chapter 1 because let me begin by saying here's the goal of Chapter 1. What's the intent of Chapter 1? And you guys heard me kind of refer to it that it's a I call it a science chapter. It's not a physics chapter. It's about making measurements and significant figures and converting units. And so if you've had a physics class, you've done this. If you've had a chemistry class, you've done this. Even a biology class, mostly you've done this. A little less math in a biology class here. So I have a feeling most of you have seen all this stuff in Chapter 1. And because of that, I may not say everything about Chapter 1, so we can actually get started in the physics in Chapter 2. So let me make that clear to you guys in person and online. Please read Chapter 1 of the college book. Read all the details. I may not say everything, but we need to at least be acquainted with it, and you probably already are here. So what is Chapter 1 about? Well, your author does a good job at the beginning of every chapter, and he gives a little outline. Okay? And so here is the outline. I kind of rearranged the outline a little bit, mostly so I could keep coming over here and say, okay, did I cover this? You know, did I talk about this? And I'm going to leave this then here and say, okay, here's what I want to talk about. I want to talk about making measurements, physical quantity, making a measurement. And then, of course, what units do you use? How do you switch to other units? Like how do we switch from meters to centimeters or centimeters to miles? The prefixes of the metric system. What's the difference between an accuracy and precision? What is an uncertainty and what are the significant figures and what are approximations? And so this whole chapter really is all about making physical measurements. And that's what we need to do. So I like to start off this way. I like to make a little chart. Let's see if I can squeeze it in on this panel here. And I like to divide it into two and say, all right, you're going to see a pattern starting today that's going to continue all semester. Actually, both semesters. And that's why I want to take a little bit of time. The pattern I'm going to go through is a pattern I think you're familiar with, but it would be helpful to recognize that pattern so that when we get to quantities you haven't done before, you'll go, oh, that's how physics works. And hopefully this will be a training exercise to get that brain to think like in terms of physics. Because, as I said, it's been a long time since I've taught this level of class, but I do remember this. It being a little different than my engineering class, is you guys are extremely bright and gifted, but you haven't spent as much time doing math as my engineering students. And so that's what I want to always keep in the back of my mind here, is that, okay, I need to sometimes just pause and remind the students who are in here about the math that they may not have touched on since their trigonometry class or since their algebra class here. And you're going to see that pattern here when we go through our different physical quantities because, of course, being a physics class, and I think this is the normal phobia that life students have, is there's a lot of math in here, isn't there? And yeah, there is a lot of math. But again, hopefully it won't be too scary for you because I know you've done it all. And I think presented in the right way, you'll go, oh, I get it. All right, so that's where this quantity is going to come in. And let me just put a little slash here and put symbol. Over here in this column, I want to put the units and the symbol because you'll begin to hopefully, in your mind, kind of separate these two, that there's always a physical quantity that we want to measure, and then there's the units that go with that physical quantity. We like to put it this way. We like to say, in this column, this is nature. This is our job as a scientist to find out how does nature behave. And so we don't invent physics. We discover physics. Now, We as humans, though, invent the units to measure them. Like how long is a meter? Or is 70 degrees Fahrenheit warm or cold? You know, that's a scale that we as humans design. And so that's an important difference between here and here. This is humanly defined. This is just nature. And it's sometimes easy to understand nature and sometimes not so easy to understand nature. And so we don't have the option or the luxury of saying, hey, this is going to be easy or hard, or let's change it, make it easy. That's just the way nature is. And so we're kind of left with that. So here's where I begin. It's almost boring in the sense that you've done it so many times. It's the whole reason I brought out this table. I'll move the table because I know that my lighting gets real funny when I get in front of the projector here. But I've got a meter stick. Okay? And so one of the first things that you probably learned back in kindergarten without even thinking about it, and I'll say humans, way back when they were cave people, started asking things like, well, how far is it? You know, how far is it from the front of my cave to the watering hole? I'll keep it simple here, and I'll just say, well, how far is it from this edge of the table to this edge of the table? But as a young kid or as an early humanoid, you begin to ask the first scientific question, the first thing of physics, which is this quantity called distance. How far is something? And so your brain starts working, and the first thing your brain does is say, okay, what is the distance? Now, I'm going to put on here displacement also, only because we'll make a slight difference between those two when we get into the math details of the next chapter. But we need then a symbol so that we don't spell out distance all the time. Well, you could imagine we're also going to be mathematical, so maybe I could do something like this. You could imagine that maybe this wall over here I call my reference point. This is my origin, if you will. And so if you think of a number line, you'll come over here and say, okay, well, over here is some distance. But over here, then this distance is a little further. And so if I wanted to know how long this table was, if I called this position 1, so mathematically I might call this x1, and then over here I might call this x2, it makes sense then what I would do is I would just subtract the two, right? Maybe this right here is 4 meters away, and maybe this is 6 meters away. And so if I wanted to know how far it was, I would go, well, take that position, 6, subtract that position, which is 4. 6 minus 4 is 2, so the distance of this table is 4 meters. Well, I probably spent too much time there. You guys probably already get that. I mean, that's kind of basic arithmetic, basic number line. But that's why we're going to then use the symbol delta x. That's what I'm getting at. So we will use delta x as the symbol. In fact, let me kind of separate it into two pieces. I'll go delta x with the absolute value and delta x without the absolute value, because that's really going to be the difference between these two words, distance and displacement. And so if you wanted to know this minus this, so 6 minus 4, well, that would be 2. But if you're going the other direction, and you call this final, and this is the beginning, you might say 4 minus 6, which is negative 2. So this direction is a positive 2, and this direction is a negative 2. The distance is the same. So in terms of distance, let me just put the absolute value of delta x. But in terms of displacement, it's going to matter to us, are we going to the left or are we going to the right? And so that's why that kind of that subtlety there. Now, again, I think you probably already know this, but in science, in the metric system, what units do we use to measure distances? And I think you know it's a meter. And I think you also know the symbol for a meter. Maybe this will be a good chance to get some feedback to you. What's the symbol we normally use for a meter? Yeah, a lowercase m too, right? Okay, and so lowercase m. All right, now, see what I'm getting at here is you've come up with a new quantity. You thought about something. Now, maybe you haven't thought about it since you were in kindergarten, and you walked in the first day, and the teacher says, okay, we want to teach distances, and they give you, I know for my kids, they gave them like these 3 sticks, and the teacher said, okay, which is the longest stick, which is the shortest stick, and which one is in between? And that was kind of their first learning that month of how to measure distances and how to relate those. But for you guys, I'm saying, you probably really haven't thought about that since kindergarten, but do you see how you did your first physics way back there in kindergarten? You see how you really started this process of saying, okay, let's ask about the physical world and let's start measuring it. And then of course later on the teacher went beyond asking you which one is bigger and smaller, but was asking you to measure how long it is. So let me just take advantage of that. Let me actually take then this meter stick, and I'll put I'll put 1 meter stick maybe up against this edge right there. And then I'll take the second one, and then I will say, okay, well then how far is it? Now I think I bumped it a little bit, so maybe, oh no, that's good. A little more accurate measurement here. Maybe I would say something like it is 1.834 meters. Okay, so 1.834 meters. Now, again, I don't think any of this is a surprise to you, but I'm going to ask you this question. Why did I write it as an M? Now, part of that answer, good, and I'm glad you're pointing. You're pointing at this saying, well, because that's the symbol you use for a meter. Oh, okay. But how come I didn't do something like this? 1.834 semicolon meter. Or 1.834 comma meter. Or 1.834 slash meter. How come I put nothing in there?
Because the unit directly relates to that value.
I don't disagree with that, but there's something deeper here that if you're not familiar with, it's worth me taking a moment to point out. Let me take something a little bit bigger. This will actually kind of help on this step here, approximations. Now, this is the one that I probably don't need to say much about. An approximation means really guess. Do your best guess to figure out the number is based upon what information you have. So some approximations are really poor because you don't have much information, and some approximations are really better. So there is no hard and fast rule about approximations. So let's just say I'm going to make an approximation for the size of this room. And I'll say the width of this room. And so I'm looking at that door to my right and this door to my left, and I'm going to say, how far is that door? Now, obviously I have a meter stick, so I really could do something better than an approximation, right? I mean, I really could come out and lay this. But let's say I'm not. Let's just, to get a rough number, let's just kind of lay this out and say, okay, imagine stacking this. Maybe it'll serve me well to stand in the middle and say, okay, it looks like I could probably get 1, 2, 3, maybe 6 that way, 6 that way. We'll call it 12. Seems like a good approximation. And that's what I want to emphasize. I'll say it is 12 meters. It would be hard for me to say like 12 and a half meters, I think, at this kind of an approximation level, right? It would be hard. But again, why did I put that M by itself? Not with a comma. And so let me take you back probably to about 3rd grade and say, okay, what if you had 5 plus 5 plus 5? Maybe I'll do it one more time, plus 5. See, because probably in second grade, you were asked to add these together, and you went 5 plus 5, 10, okay, plus 5 more, 15, plus 5 more is 20. And you go 20. But when you got into third grade, your teacher said, hey, we got a new plan for you. We can write the repetitive sum as a shortcut. And so I told you this was a review. I mean, we're going all back to kindergarten and third grade here, right? Okay, but in third grade, how did you write this? Yeah, you did multiplication, right? You learned the idea that 5 times 4 meant you add 5 4 times. Fair enough? Now, when you got a little bit older, maybe that changed to y plus y plus y plus y, and you called it, but y plus y plus y plus y would be 4y, because again, what you're saying here is take a 4, multiply by the y, right? Because 4y means repetitive addition. It means add y 4 times. Now, why am I doing all this? Because what does this really mean? What does 12m really mean? It means you have a meter, and then another meter, and then another meter, and then another meter. How many meters do I have? 12. And you're saying, take the meter and just take the m and add it 12 times. Now here's what I'm getting at. When it comes to units and converting units, please remember that that m is not just a word off to the side. That is an actual symbol, and it can be used with the same rules of mathematics that your numbers can. That's where I want to start here today. So everything that you've learned in your math class that you do for numbers, we will also do for our units. If you ever come across something that is complicated, you go, what do I do? My answer to you is going to be, what would you do if they were numbers? Do exactly the same thing. So that's what I want to emphasize, because you may not have seen 12m quite in that fashion. 12m actually means take the number 12 and multiply it by the symbol m. Because it really means I'm going to add m 12 times. That can be very, very helpful. And hopefully you'll see that here in this first chapter. How powerful thinking about the units obeying the same rules of mathematics as the numbers. And that way, when we start to do things you haven't seen before, I mean, I'm doing things I presumably you've seen, measuring the distance. But when we start doing things like farads, amps, coulombs, maybe those are words you've never heard, and that's good. But I can guarantee that if you just follow the simple rules of mathematics for the units that you do with the numbers, it won't give you a hard time. A phrase you're going to hear me say a lot is this: physics is about knowing how to apply a few, literally, I mean that more than anything else, few powerful fundamental concepts to explain a universe of ideas. Now, especially for you guys in life science, I want to emphasize that, because I think as you come from the life sciences, you come with a different approach. You come with a lot of memorization, a lot of materials. That is not the approach for a physics class. Physics is about a lot of deductive reasoning, and that's where I want to start here today. And with this very simple third grade idea is there's not going to be a whole lot of memorization. There's going to be a lot of deductive reasoning. And you'll hear me say, this is about taking a few powerful, but few fundamental principles to explain a universe of phenomenon. When it comes to all of our motion, we'll say I can explain all your motion, where it's a satellite or a molecule, in 3 sentences. Newton's first law, second and third law. You give me that and I can tell you everything about that satellite, everything about that rocket. Sure, it's going to take me 5 pages to do the homework and work out the details of what the thrust is of that rocket. But that's what I want to emphasize. Those 5 pages are not memorized material that I'm regurgitating down. Those 5 pages of detail are just 2 or 3 sentences of memorized material. The rest is detailed, deductive, mathematical reasoning. And so keep that in mind, because that is powerful. And that's my goal, is to, of course, teach you about physics. And that's where physics is very different than the other sciences. It's not a lot of memorization. Very little memorization. And in fact, you'll probably find yourself, and I'll keep warning you, that you're memorizing too much. And I'll say, stop memorizing so much. Start working out the details. Okay, well, let me keep going, because I hope that really helps here, because it will, as you begin, mean that I don't have to memorize all these units about a Faraday and a Coulomb. I just need to work out the details of where they came from. And that can't be overemphasized. All right, well, let me clear this off a little bit. Let me take this maybe as an opportunity to turn that off for just a second. We'll come back to it. But what this then is telling me, if we go back to the length of this table, is I now have a certain length to my table, listed in, of course, meters. Now, let's talk a little bit more about what we mean by this number. Because again, this is this goal of this first chapter. What do we mean by the units and what we call the prefixes of the metric system, and conversion and accuracy and uncertainty? All right, so if I stand back and I look at this number, well, one of the things I might ask myself, and this is the really neat thing about the metric system, and probably don't need to spend much time here because I think you are there already, is what is then a centimeter? What is a, go ahead.
It's 10 to the negative 2 meters.
Uh-huh. So it's 100th of a meter, right? Oh, what is a millimeter?
10 to the negative 2 or 1,000.
Okay, so there's 1,000th of a meter. Okay. What is a kilometer, better pronounced as kilometer? Now, I think you guys all know this one, but just in case you don't, this is what we mean by the prefixes. And so the neat thing about the metric system is when you are measuring distance, if you know the base unit meter, any other unit that measures length will have the word meter in it. And so we know already, by just looking at these words, that every single one of those measures distance. It's a meter. The prefixes then tell us what that number is. And so as you pointed out, the centa means 100. The milli means 1,000. The kilo means 1,000. And let me take this as an opportunity then to use one that's not very common. You ever heard of megameter? Some of you saying yes, some of you saying no. But here's what I'm getting at. If you had never ever heard of the word megameter, you know right away it measures distances because it's got meter in it. And you know whether it's a big measurement or a small measurement if you know what the prefix is. And so mega is a prefix that means, does anybody know? Yeah, a million, 10 to the 6th. Mm-hmm. And so 1 million. And so the neat thing here about the metric system is I can quickly then figure out what is the connection between the base unit, the meter, and any of the prefixes ones because of, that's where the metric system is set up, I guess. And I guess I should say in comparison to, say, the English system. If somebody asks you how far is a mile, anybody know how far miles?
It's like 5,680, something like that.
Very close, yeah. 5,280 feet makes 1 mile. But see, there's nothing in the word mile that would indicate that it measures distance. And there's nothing in the word mile that you were going to come up with 5,280. You just have to memorize it. See, this fits my pattern. We don't want to do a whole lot of memorization. We know now that I could come over here and put femtometer, nanometer, gigameter. Maybe I'll just do gigameter on the board. Gigameter. But again, right away, meter. I know it measures distance. Giga. Now, granted, you do have to memorize something. You have to remember what the prefixes are. Anybody know the giga? That's a billion, right? 10 to the ninth. So giga would be 10 to the ninth. So why don't I take this as an opportunity to point out that your author, right here on the beginning part of the chapter, gives you a chart of all these wonderful prefixes. I don't expect you... Wait, where is it? I don't expect you to memorize all of them, but I do think that you will come across centa and milli and mega and giga so often that those are probably worth committing to memory. And so here's the table, and here's the milli, here's the centa. I guess I didn't say micro, that was a good one. I did mention nano, so that would be 1/100000th. What I actually put on the board was the other direction, giga. Maybe it's up there. Where's giga? Yeah, right here. And so giga is the billionth. Okay? And so the prefixes, I think, speak for themselves, but they're so wonderful and easy to use that's why we choose to use them in our science class here. Now, let me keep going here, because centimeter then is going to have its own symbol. And I picked this one first because I think you're familiar. What's the symbol for centimeter? Well, cm, although I'm going to change this a little bit. Do not think of it as cm for centimeter. It's actually a C for centa and m for meter, with nothing in between it. Because what it really means is 1/100th of a meter. The C can be replaced with its mathematical number. Right? So if I wanted to convert, if I told you that something had 7.5 centimeters, and I asked you, how many meters is it? God, this would be so simple, because it's replacing the centa with what it means. You would just go, well, it would be 7.5, and in place of centa, I'll put 100th of a meter. There it is, right there. If I wanted to switch it right to a meter, it's a really easy step. And so, of course, times 10 to the minus 2 means move the decimal 2. And so the answer would be 0.075 meters. That's how I would convert it. Now, those are probably the easiest conversions. But hopefully it fits this category where I'm trying to get you to see what the prefixes are. You see how you convert them? And what if I had this? You know, if I had, how about 14 GM? Whoa. Whoa. And I asked you, how many meters is it? Well, hopefully the first thing you recognize is this is a prefix in front of meters. So this is a length. And then this right here, this giga, is obviously some prefix which you may or may not have memorized, but I keep saying giga, so this is the symbol for giga, and giga means a billion. So if I wanted to say how many meters is it, I guess I'd go 14, and then this would be 10 to the ninth. And so I guess 14 times 10 to the ninth might be one way of writing it. I guess another way would be 1.4 times 10 to the 10th meters. And I guess another way would be to go 14, comma, 0, 0, 0, comma, 0, 0, 0, comma, 0, 0, 0. Okay? And so whatever you want to do with your numbers, all of these are fine, but do you see how the prefix makes it so incredibly simple when you use the same rules for your units that you do for your numbers? In other words, you can convert a number into a symbol like a centa or a mega, or the symbol mega or giga into a number. And that makes converting units really, really simple in the metric system. So as long as I'm here, I might as well point out, since I did say giga, so gigameter would be the symbol there. But I wanted to do one that was probably uncommon to you. And if you've never seen a capital GM, you don't really need to memorize it. You would just say, well, I understand how the metric system works. That little m at the end must be a meter, and so this must be measuring length. So there's your giveaway clue. And then that prefix is giga. Now that you have to memorize. You have to say, okay, giga, what does it mean? It means a billion. But now I know it measures. Even though I never heard the word gigameter, I know it measures distance. And I know it measures a long distance. It's 14 billion meters. In fact, maybe I would use this as an opportunity to say, you know what, maybe I want to know how many kilometers this is. And so maybe I'll take those 3 zeros and treat it as 10 to the 3. So this would be 14 million times 1,000 meters. But 1,000 meters is a kilometer. 14 million meters. And so I'm using the symbol kilo, which is right here in my math. And so, again, do you see what I'm doing here? Do you see I'm using the same rules of mathematics for my units as my numbers? Mm-hmm. And keep that in mind. It can really make things really simple. Yeah?
Why are you guys reading with capital G?
Oh, giga.
Others are written with like a small letter.
Yeah. So for a little bit of historic reasons, anything bigger than 1,000 uses the capital letters. So mega is a capital M. Giga is a capital G. Tera is a capital T. Okay? And anything smaller than 1,000 uses the lowercase. So kilo uses a K. Milla uses an M. Centa uses a C. Maybe I should put the meter with it. Meter. What would be smaller? Centimeter. Micrometer. Sadly, micro starts with an M. And starting with an M could be confused with the milla. So we put a different, and we go to the Greek alphabet on that, and use the mu in the Greek alphabet. Oh, by the way, though, did you notice that even though we used the lowercase m for milla, that didn't bother us with the lowercase m for meter? See, those were separate. Those were two different categories. So there was no confusion, hopefully no confusion. Obviously, a beginning student, there could be confusion. But we run into this a lot where we go, okay, I've used this symbol before. Is it okay? Yes or no? And if you've used it in the same category, the answer is no. But if you haven't used it in that category, then the answer is fine. So there was nothing wrong with using this for millimeter. I could also do milligrams. That one might be more appropriate for you guys in the life science, because you say, hey, I took an Advil this morning. It had 200 milligrams of ibuprofen, you know. And so, but notice that M would clearly stand for the milli, not for the meter. And of course, we could run into troubles if we put another M here for micro. And so that's why we definitely changed the symbol there. So I know I got way past your question, but thank you for asking it because it was a good question, but I expanded on it. But anyways, capital letters, mega and bigger, lowercase, and that's just a tradition. Nothing real fancy there about it. All right, but let's keep talking about here converting units. All right, so I'm converting units, and I've been doing it so far within the metric system. And that's probably the easiest way to do it. Now, I was showing you how to switch the symbol directly, but let me show you kind of a more routine mathematical approach that will be very useful. And so let me come back over here to this measurement. How long is the table? And let me ask this. How many centimeters is it? Or a better question, how many inches is it? Okay, so here's going to be our strategy. Start off with the known length. Okay, so I know it's 1.834 meters. Okay, so that's the known length. And if I convert it to centimeters or inches or miles or even light years, whatever I use to measure the length, you must remember the length physically doesn't actually change, right? The thing that changes is the unit, but remember the unit goes with the number. Remember they're multiplied together? See, as silly as this sounds, I'm asking you, look, if I had the number 12, you could say the 12 is 6 times 2, but that's not the only way to get 12. Right? You can change the 2 to a 3, but then of course you got to change the 1 in front, so it's 4 times 3. And I'm going to say the same thing. I'm not going to actually change the length. It's going to be the same length. But if I change this number, I got to change that number. And of course, I got to change it by the appropriate amount so that the 2 multiplied together is still giving me the same number, just like this 12 did. Okay? So here's my suggestion. Think of it as taking that number and multiplying it by 1. That sounds weird. I mean, it's so basic. You multiply by 1, what happens? Right, it stays the same. Fancy word in mathematics, we like to call this the unity operator. Right? Whatever you do, when you multiply by 1, you get the same thing. Kind of boring. But that's my point. We don't want to change the length. We just want to change how we examine the length, how we view the length. And you can do that when you multiply by 1. But it needs to be a clever one. Well, watch this. Over here on this part of the board, I'm going to put 100 centimeters is equal to 1 meter. Okay, so that's the conversion. Now, let's think about my goal. What is my goal? My goal is to make sure I take this length and I don't change it. That's why I'm multiplying by 1. So I don't want to change the overall length, but I do want to change the units. I want to change it from meters to centimeters. Well, let me remind you, again, maybe back to 3rd grade of a little bit of math. What would 5 over 5 give me? 1. Right? Anything over itself is 1, right? For that matter, 5 over 2 plus 3 is what? 1. A over A is 1. So there's a lot of ways to write the number 1. And notice that when you have the same thing above and below, it is equal to 1. Sometimes we say it cancels off. Like if we had 4x over 3x. Well, they cancel off. Which I don't think is a very good word. They don't really cancel off. You said x divided by x is 1. And then 1 multiplied by anything else doesn't change it, so I don't have to write it in the equation. And that's what I'm going to say here. Watch this for a moment. Let me multiply it by the number 1. And to be a number 1, I have to put whatever is on the top equal to what's on the bottom. But also keep in mind what I'm trying to do is get rid of the m. And I'm trying to get to centimeters. There's your clue. My suggestion is when we're converting units, think about the units first, not the numbers. See, here's what I want. I want to get rid of this m, and the way to do that is to make sure I have an m down here. And I want it to end up as centimeters. So that means I want a centimeters in the top. That's really the magical step, is to go, how do I want to put my units? I want meters downstairs, so that'll cancel off. And I want centimeters upstairs, so that I'll be left with centimeters when I'm all done. But I also have to remember that this whole thing has to equal 1. So whatever's in the top has to be the same number in the bottom. Well, that's perfect, because isn't 100 centimeters the same as 1 meter? That's what this statement is saying. And that's my key for you when you ever get a question that says convert units. And in tonight's homework, you're going to get that a lot. Tonight's homework is going to say convert these units. And so here's what you're going to do. Start with what you have and put that in the bottom. And where you want to go on top. Because when you do the math, and I'm going to say it again, do the same thing with your units as your numbers. So if I put my numbers together, 1.834 times 100 divided by 1 would be 183.4. And do the same rules of mathematics with your units. That's why I was making such a big deal out of A over A is 1. Because when I come over here, what is a meter over a meter? 1. You might take cancels. Goes away. What are you left with? Centimeter. And there it is. Now let's take this a step further. What if I asked you how many inches this is? See the same game? What do I want to do? Multiply by what? I'd say multiply by 1. But what do I want in the bottom? I want centimeter. What do I want on the top? Inches. So what you want on the top is what you want to get to, because you want this to cancel off. Now, for it to work, you have to be multiplying by 1. So you have to have something up here that says so many inches, but it has to be equal to so many centimeters. Now, of course, this is a conversion that I wouldn't encourage you necessarily to have memorized, because now we're getting out of the metric system, and so we don't do that too often, but we do it often enough that we need to know how to convert from the metric system over to the English system. Anybody know how many centimeters are in an inch? Yeah? 2.54. Good. Centimeters make exactly 1 inch. All right. So this is the part that you might have to go look up, like how many feet are in a mile, or how many yards are in a chain. There's one that I'm sure everybody knows, how many yards are in a chain. Use that, such a common word. But you'll see here, if I play that same logic, the centimeters would cancel off, and I'll leave the numbers alone for a moment, because I know you guys are good with the numbers, and you got a calculator anyway, so the numbers usually aren't the student's problem, it's the units. What are you left with? Inches. And so now I could go 183.4 times 1 divided by 2.54. And so this would be 72.2. And I'll go 0 inches because we want to talk about significant figures here. And actually, sorry about that. I should do this. And no, it should be this. Sorry. That's our next step. But how many significant figures? So I shouldn't have brought that up quite yet. I didn't want to quite get to significant figures. I just wanted to point out here that what I'm doing here is right here, converting units. Okay. Well, I should keep going because I want to show you a bunch of these, and I got some examples to work out for you here, and so you'll get the hang of it, or you'll ask me a lot of questions in lab or in Zoom, and we'll go through because you're going to be asked to convert a lot of them. And like I said, here's the magical key. Think about what you have and where you want to go. Put up here where you want to go, so it cancels off with what you have. Sometimes you might have to do 2 steps this. For example, if I asked you how many seconds were in a week, what would you do? Well, I guess I'd start off and go, 7 days is a week. Right? Okay. And I don't want to change that number. Now, when I say number, I mean both the number and the units. I still want it to represent 7 days, but I want it to be represented in the number of seconds. So just like this 12 over here, I can change the number out in front with the units behind it. Right? They're multiplied together. So changing one affects the other. So I'm going to multiply it by the number 1. Now, I don't know how many seconds are in a day. Actually, I do, but pretend I don't. Okay, so I don't know how many seconds are in a day, but I do know this, that I want to get rid of days. So I'm going to put it downstairs. Now, I ultimately want to get the number of seconds, but I could at least go an easier calculation and convert it to how many hours. You see how I did the units first, right? And I put down what I want to get rid of down here and what it becomes up here. So now what's going to happen is days is going to cancel off, and if I just did this multiplication, it would give me hours. But of course, remember, for this to work right, I really need to make sure I multiply by the number 1. So I need to make sure what's in the top is the same as the bottom. So let's see, 24 hours is 1 day, right? Okay, so that technically didn't change a week. It just changed it from listing it as 7 days to now listing it as so many hours. And I won't even bother to do the multiplication yet. I'll just tell myself that what I've done right now is convert it into hours. My ultimate goal is how many seconds. So I do want to get rid of hours, so the next step I'm going to do is put hours down here, hours. Say, okay, let's get rid of hours. And convert it to what? Well, again, ultimately I want to get to seconds. And I do know how many seconds are in an hour. You probably do too, but let's pretend we don't. But I do know minutes were a little easy, so I could put minutes up here. Right? And see, that would then get rid of my hours, and if I multiplied this all out, now I would have how many minutes? Now, let me emphasize, again, this only works if you technically have a multiplication of 1. So I need to make sure that what's in the numerator is the same as the denominator. All right? So what I know is 60 minutes is the same as 1 hour. See, so I started with 7 days, and I multiplied by 1, and I multiplied by 1. I haven't changed it. I still have 7 days. I still have a week. But I have a week listed right now. If I stopped and did the multiplication, I'd have it in minutes. So I'm going to do one more step. Because I ultimately want to get to seconds, so I want to get rid of minutes. So downstairs I'll put minutes. See, so those are going to cancel off. And I'll put up here seconds. And so let me say it again. I think the best way to convert units is to think about you're multiplying by 1. And put downstairs first the units you want to get rid of, and upstairs what you want it to become. And then think about the numbers to make it 1. And of course, I think, as you know, there are 60 seconds in 1 minute. So I've got 7 days multiplied by 1, multiplied by 1, multiplied by 1. So I still have 7 days. I still have a week. But I have a week that, as you'll see, minutes will cancel with minutes. And after all this mathematics, and I'll say it again, use the same rules for your units as you do for your numbers. You will now get this into seconds. So grabbing my calculator, I can start here and go, this would be 7. Here I would multiply by 24 and technically divide by 1. I won't bother to actually do that on my calculator. And then times 60 and then divided by 1. I won't bother with that since that doesn't change anything. And then right here times 60 again and then also divided by 1. And then equals. And so this comes out to be 604,800 seconds. All right, well, maybe that's enough for right now. I'll do some more examples of converting units, but I probably should start addressing here uncertainties and significant figures here. These are kind of one and the same. Let's go all the way back to the beginning here. When I wrote this down, and of course maybe now I can erase this stuff here, and maybe now it's making more sense to you why I said we write it this way so that we can do the same rules of mathematics with our numbers as our units. They're part of that pattern. But here's where I want to emphasize something that traditionally has given students a hard time. It's significant figures and uncertainties. And I think the biggest reason why is, I like to say it this way, our numbers in science are not the same as in your math class. What? What do you mean by that? Here's what I mean. In a math class, if I wrote down 1.834, this is what I would mean. 1.834000000000000000000. That's what it would look like on my calculator. But see, in science, that's not what we mean. When I came out here and I measured the actual length of this table, what did I actually mean? Well, I meant it was more than 1 meter. It was 1 point something. See, I had one whole meter stick here, and then I had a little more. Okay? In fact, I know how much more because I'll tilt it this way. You can see that this thing reads to a thousandth of a meter. It reads to millimeters. So I can see this 83.4. So in other words, I know that it was more than 1, but not quite 2. It was 0.8. Now, it was even more than 80 centimeters. It was actually 83 centimeters. In fact, it was even more than 83, but wasn't quite 84. It went to another one. But what about the next decimal place? I guess I'd call that a tenth of a millimeter. I don't know what that one is. And I don't know the next one, 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 and I'm going to pause. Do you see the difference between these two numbers? See, in a math class, you're saying, oh, I know all those numbers are 0. That's not what a science class is trying to say. A science class is trying to say, we know up to a certain precision. And the numbers beyond that are unknown. They're not zeros. We just don't know what they are. See, and that's why we have these little rules on how to treat these unknown numbers that aren't the same on your calculator. that are not the same that you learned in your math class. And you say, ooh, how long is that? See, here's why it makes a big difference. Let me clear this off a little bit here. And say, okay, let's say that I'm going to take a scientific measurement and I have gotten 3 objects and I'm going to measure their length individually and then stack them together and say, how long is it? Now, I'm sure in your head you're going, well, that's pretty simple. You're just going to measure them and then add the 3 together, right? Sure, I will do that. Let's give it a try. I'm going to start with this one. I'm going to measure its length. But I'm going to use this meter stick. I don't know if you can see, but this meter stick has tape over it. I can't really read all the other numbers. All I can see is 10 centimeters, 20 centimeters, 30 centimeters, and 40 centimeters. That's 1/10 of a meter. So I'm going to measure the length of this and say, okay, this first one, maybe you'll even kind of hold it towards you. But this first one seems to be more than 60, but not as much as 70. So that means it's 0.6, but not quite 0.7. So let me call this length number 1. And I'm going to call it 0.6. Now I know it's more than a 0.6, don't I? But it's not a 0.7. So what I'm going to do is take a rough guess. It's a reasonable guess, but it clearly is a guess on how far along is that next one. So it looks like 6.5 would be right here. And sadly, this isn't cut very smoothly here, but I'll do this edge. So maybe that's a 5, that's a 4. Maybe it's close to a 5. Maybe it's a 4, but I'll call it a 5. Okay. So I'm going to go 0.65, and then what? Well, there's no way I can guess the next ones. But I want to emphasize to you that this is a science number, not a math number. So I want to put question marks in there. I want to emphasize that I do not know what those next numbers are. If I had something that I can measure a little more accurate, which I do, I could tell you what it is. But let me not do that. Let me go on to my next object. So let's take this object. Okay, now this object, I'm going to use this meter stick. I don't know if you can see from your distance, but there's tape on it, so I can only read to the nearest centimeter, but I can't read the millimeters. So if I laid this out and said, how long is it? It looks like here's 40, here's 46, and it looks like it's a little more than 46, but certainly not a 47. So the length of number 2 would be 0.46, and clearly it's more than 0.60. At least clearly from my perspective. I know you guys are a little far away, so you might not be able to see it, but it's not a 7. It's not even halfway. It's barely past the 6. So I'm going to call it a 6.1. But there's no way I can make even a reasonable guess at what the other numbers are. So they have some numbers, but I want to emphasize, they're not zeros. See, this is what we call significant figures. This is what we in science then say, what numbers do you actually know, or at least reasonably know? So when I looked at this, I would say, well, the zero is just kind of giving a marker, so that does not really a measurement, but these two are. So I would say I have 2 significant figures. That make sense? I've measured two numbers. I've measured not only to the 10th of a meter, but then approximated the next one to 100th of a meter. But my other measuring device was more precise. Right? It did a better job. It actually had marks on it to 100th of a meter. And I could reasonably guess 1,000th of a meter. But there's no way I can know what this 10,000th is, or this 100,000th, or this millionth. I don't know what those numbers are. Now, I said I was going to do all three, but in the interest of time, let me stop right there just to kind of illustrate my point. What if I put those two together? Then I asked you, how long is this? Well, I'm sure you're thinking, well, just add those two numbers together. You got the individual lengths, you just add them together. Okay. But look what happens when I add them together. Way out here, if I add an I don't know and an I don't know, what do I get? An I don't know. And same here, I don't know. I don't know. I don't know. I don't know. This is the interesting one. What do you get right here when you add these two together? Take an I don't know and you add a 1. What do you get? You still don't know. So it's tempting to put a 1 there. But remember, if you put a 1 there, you have just called that a 0. You have just thought of your number as you would do it on your calculator. This is why I like to say you got to be smarter than your calculator. Your calculator, believe it or not, is not as smart as you. Your calculator is going to treat that number as a 0, and you need to make sure that you understand what you're doing with your numbers, because your calculator won't help you on this. You put those numbers in your calculator and hit enter, it would give you a 1 there. But what I'm trying to say is we really do not know what that number is. And this is what we mean by this phrase, significant figures. Which ones are actually useful numbers? Because all these other zeros are not useful. Your calculator thinks it is, but you don't know what those numbers are. Now, what happens when I add a 5 and a 6? I do know that's an 11. So I'm going to carry 1. And then I would have a 1 and a 6 and a 4. I guess that makes 11. So a 1 and carry a 1. And I get a 1. And so the correct answer when we're all done with this is the length is 1.11. Oh, yeah, and sorry, and all these were meters. Thank you, Ron. Meters, 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 meters. Yep, I mean, don't forget that. That's the whole point of this chapter here. Okay. But notice it is not 1.111 meters. Notice these are not the same numbers, right? Notice that and that are not the same number. So what we call significant figures right here is our way in science of distinguishing between what numbers we know and what numbers we don't know. Okay? And so you can see in this general pattern here that we like to say this. When you ever add two things together, your answer right here has to have an answer that has no more higher precision than the least precision one up here. And so the least precision is this first one. 2 decimal places. Our answer then can only have 2 decimal places. We were making a mistake if we ever tried to give an answer with 3 decimal places, because that means we've treated this as a known number and we don't know it. All right, so our rule, keep in mind, is every time we add some numbers, we're going to pause and we're going to look at how many significant figures are there, and our answer will have the same precision as the least precision one. If I had another one up here that was, say, 0.7, I don't know, I don't know, I don't know. See how that I don't know would make this an I don't know. Okay. Now you could do an intermediate step and add these two and carry a 1 over, and that would be justified and then, but ultimately you would have to end up with an answer that has the same precision as the least precision number. Okay? Now, I won't bother to show you the same thing happens in subtraction, so let me just say, if we add or subtract numbers, the number of significant figures has to have the same precision as the one at the end. Yeah.
Isn't the amount of significant figures different than the precision? Or am I confused? It's like, wouldn't that number have 3 significant figures, but the least precise is 2 decimal points?
Yeah. So forgive me, I might not have said that very clearly. Sorry. What I mean to say is the answer has to have the same precision as the least precision. Right. And so to make it clear, so the least precision is 2 decimal places. That's why I have it, but I do have 3 significant figures. Yeah. Thank you. I was beginning to say it like we do for multiplication, and that's where I want to go next. So I apologize here. All right. So with that in mind, I probably shouldn't dwell too much time on this either, because especially those of you who were telling me you've gone through chemistry already, the way our program is set up, you'll get hit with this really hard in chemistry. Is that true? You guys went through chemistry? Yeah. And they'll really hold your feet to the fire. And so because of that, we don't too much. If I see you violating the significance figures rule, I'll just say, hey, careful here. And I won't take any points off. I'll just say, look, you know, our numbers are important the way we treat them, but right now we're focusing on physics, so I won't worry too much about your significant figures, because I know you will learn that in chemistry really well. Because I know in chemistry, if you don't, you lose a lot of points on it. So that's kind of how our program is set up. So don't stress it too much in this class. Save that stress for chemistry. Okay. Now, let me keep going, because I've been talking a lot here about this number, and I want to come all the way back to this chart, because I've been trying to kind of set up our thinking process and say, okay, now what do we want here with our next step? And so let me ask you this. Again, this is probably something you did, maybe not in kindergarten, maybe it was first grade, but you said, all right, how much then surface area is on this table? So instead of doing the length only, you start thinking about the next physical quantity. You go, hey, wait a minute. There should be not just a distance or a length of this table, but there would be this idea of an area. Oh, it just dawned on me. This is probably a good time to take our break. Actually, past the time. So why don't we hit pause there, Ron, on the camera, and take a 15-minute break. I meant to do that at, what time did we start? 8? So 8 to 9:30. Anyway, so somewhere around the 9:30 time, we should take a little break, anyways, keep going. So why don't we take a 15-minute break and stretch our legs and take a breather and come back, and then actually we only have 50 minutes left after that. So, all right, and we'll finish up the chapter. All right, hey, welcome back from the break here, and let's continue on. And maybe I'll go a little bit faster so we make sure we wrap up this particular chapter. I did want to just repeat what I had said earlier. Oh, let me deal with this door. But I probably won't get a chance to cover everything. So let me emphasize, read all the chapter there, because I think our time is best spent finally moving into chapter 2 and getting started with the physics. But I do want to come back to where we left off before the break. And I started saying here about the area. And again, not being probably too new to you, but if I was just kind of going through your education as a young person or human as they've been discovering the next quantity, after measuring the length of this table, your attention may switch to saying, what is the area of it? Let's say you wanted to cover this with a piece of carpet or something, and you're like, okay, how much do I need here? This is a whole new quantity. This is what I'm saying. This is kind of a step up from distance. In our day, we'd call it maybe two-dimensional. We say, okay, we've got two pieces of information here. And so we need to then realize that here's what we're doing. We're thinking in terms of physics. We're thinking about the next question. We've gone from what is length to what is area. And of course, we got to give it a name, so we call it area. We got to give it a symbol, so we'll use the capital A. We'll save the lowercase a for acceleration in the next chapter, that's why. And then here's the big thing, what units do we use? Now, before I answer that, I guess I would say then, this new thing that we're thinking about called area, how would I get the area of this? Now, I know way back in 5th grade, you learned that length times width is area. So you might say, well, we got to get the area. It's length times width. But let me ask you this. What if you never went through 5th grade? What if you've never been told area was length times width? Could you reason this out on your own? And I think what you're saying here is an area would be some length. Let me take a meter this way and maybe a meter this way. And then another 1 meter and 1 meter. Now, if this table was bigger, maybe this direction would go further. Maybe this direction would go further this way. But here's what you're really saying. You're saying take the length and add it, how many times? The width. So if the length is 3, you're saying add 3, and if the width was 2, you'd say 2 times. It's repetitive addition. Repetitive addition could easily be written down as multiplication, and that's what I'm trying to say here, is if you had never seen this equation before, isn't that how you would work it out? I'm going to say it again. Physics is about knowing how to apply few powerful, fundamental principles to explain a universal phenomenon. Now, I'm not asking you to forget the equation for area. You've been told, great, you've probably memorized it, keep that going. But what I am saying is we're going to get into some new quantities that I'm going to ask you, let's ask a question. Let's ask a question and get a new quantity. And once we get that new quantity, we're going to say, what's the formula for it? And if we think about what we're asking, in other words, we're taking our thought and changing it into an equation. That's a hard step. That's the step that I'm guessing, both you guys in person and online, people who are in the life sciences, this gives them the most phobia. It's like, oh, you want me to come up with my own equation? And I'm going to say, yeah, sure. Mm-hmm. Change your thoughts, change your words into an equation. That's that dreaded algebra class, when you say, oh, it's a word problem. I did really good on the test except for the last problem. The problem was a word problem. And I don't want to scare anybody, but physics, every problem is a word problem. And so that's the skill we need to start. And that's the skill I want to bring you guys up with, is to say, what have you been doing? What does multiplication actually mean? What does exponents mean? What do logarithms mean? Oh, here's a tough one. What does an integral mean? And so take these principles of mathematics, and once you have a thought, you can change that thought into an equation. Of course, that's what you've been doing a lot in your math class, and we're just going to continue on doing it here in a physics class, is to take your thinking and convert it into an equation. And so this is my way of hopefully not being too boring, but also being way back to 5th grade by saying, look, if nobody ever told me that the equation for an area was length times width, I could reason it out, because what I'm really asking to do is add up the length the width number of times. Repetitive addition. Repetitive addition is multiplication. That's why I know it's an equation. So had nobody ever given me this equation, I could figure it out. And that's what I'm going to try to encourage you and hopefully train you. And by the end of these 2 semesters, hopefully you're going to be pretty good at that. You're going to say, oh yeah, I could take the thinking process, the words, and change it into an equation. And hopefully even the other way around. I see an equation and I can read it and change it into words. So it's not just do the math. I like to say, you need to read the math. And so if somebody gave me this equation from the beginning, I'd say, oh, you're asking me just to add L W times. That's what you're telling me to do. L plus L plus L plus L plus L. And I'm just going to add L W times. That's exactly what it means. And so I will read the math. Well, let me keep going here, because in our case then, we already said the length was, oh, and I already forgot, was it 1.834? 34? Okay, so 1.834 meters times, and so let me come over here and do the width. Now I'm going to use this meter stick for the width. No, actually I'll do this one. So this one reads to 1/10 of a meter. And I'll guess the next one. So when it comes to width, I'm going to go, it's more than 0.7, but not quite 0.8. 0.5 is about this, so maybe that's about a 0.6. So I'm going to guess at the last one, and so 0.76 meters is the second number. And so here I want to show you 2 things. The first one is, when I do the multiplication, the numbers are simple. Got a calculator for that. All right. 1.834 times 0.76. And I come up with 1.39384. And I have 2 horrible mistakes right now. Yeah, and the first one we talked about before the break, significant figures. Now, maybe without proof, we're going to say this, that when it comes to multiplication and division, we'll count up the number of significant figures. This is where I kind of got tongue-tied before the break. And the answer will have the same number of significant figures as the least significant figures of the product or quotient. Okay? Whereas the adding and subtraction, the precision was the focus. And so I kind of mix those things. All right. So there's one rule when we add and subtract. We add and subtract, we look, and the answer has the same precision as the least precise one. Not necessarily the same number of significant figures, as you point out. When it comes to multiplication and division, without proof, so we can move on to make our unknowns be satisfied. Remember, this is actually unknown, 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 unknown. This actually means unknown, 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 unknown. And when you multiply them out, that means some of these are actually unknowns. That's why I'm trying to say, if all I did was enter in my calculator, that would be wrong. Because that's treating my numbers as math numbers, not as science numbers. And so our rule will be, see how many significant figures do you have? Find the least, and that is what your answer has to be. In other words, your answer can't be any more than accurate than what you put into it. So in this case, I have 4 significant figures, 1, 2, 3, 4. In this case, I have 1, 2. So I can only have 2 in my answer. And so rounding that to 1.4, then this should be an I don't know, I don't know, I don't know, I don't know. I'll say it again, because these I don't knows multiplied with those I don't knows means you really don't know what those are. Just because your calculator gave them, remember, your calculator is treating those as zeros. And so your math number and your science number is not quite the same thing. So the best answer I can give is 1.4. And that's how we'll do it, meaning the rest of these are I don't know. And of course, I'm also missing something else real here. What's the other big mistake?
Meters.
Yeah, the units. And what am I missing here?
Oh, meters squared.
Oh, good. Now, did you catch that? If this was the first time you've ever done area, if you just follow the rules of mathematics, if you have an m times an m, what do you get? M squared. So this m times that m makes m squared. And what I'm hopefully getting you excited about here is if you never ever were told what are the units for area, your thinking about the concept of area, which your thinking leads to the formula for your area, which then leads to the unit for the area. Nobody needs to tell you that area is in meters squared. You've reasoned it out yourself. Now again, I'm not asking you to do this for this particular quantity. But what about some new quantities that we haven't come across yet? Force, energy, charge, capacitance, inductance. Hopefully a lot of words you haven't been exposed to yet. But we're going to go exactly along this pattern. We're going to think about a new idea. We're going to get a formula. We're going to work out that formula, and that's going to tell us the units. Now we can maybe call them something. Let's call them square meters. Okay, so I'll give it an actual name that I can spell out. But the symbol will be a square meter. And then the last step is, don't forget that we should probably then give an interpretation of what do we mean by a square meter. And I hope this one's pretty straightforward. I mean, a square meter just means something that's 1 meter by 1 meter. Clearly, it's a surface. Clearly, it's measuring area. It's not measuring length. It's not measuring volume. It's measuring area. And so if I had a meter stick by a meter stick, that right there, 1 meter by 1 meter, is what this means. This means 1 square meter. And this is saying I have 1.4 of them. So maybe I have another piece. And that is kind of the visual picture of what I mean by the surface area of this table. 1.4 square meters. And so hopefully all that comes together, because what if I said, what is the storage space under this table? I would be asking another physical quantity. And one you've already seen in 5th grade, it would be volume. But how would you get it? Especially if you've never been told this formula before. Do you see how you would say, well, take the area of the surface and add it a bunch of times. You might call that add it to the height. Right? And so then you're going to say the volume then is the length times the width, there's the area, and then times the height. And that's how you got that formula in 5th grade. You probably didn't I doubt if you were asked to work out the formula in 5th grade. You were just given it to you. But it's then also why, what would the units come out to be? To save a little time here, let me not actually measure the height and just say, what would the units be?
Meters cubed.
Right, I would go meter times a meter times a meter, and I would get meter cubed. So again, had I never been told what are the units to measure volume, my thinking led me to a formula which led me, by following the rules of mathematics, to what the units must be. And of course, we'll use the symbol capital V for volume. The reason being lowercase v will say for velocity. And of course, then we would call this a cubic meter if we wanted to spell it out. And we should also always get a visual picture of what do we mean by 1 cubic meter. Well, we mean a little box that would be 1 meter by 1 meter by 1 meter. And so we'd have our cubic meter. Well, this is probably a good time to wrap up the chapter. I'm going to say maybe one more thing here, that under this quantity, we might put something like the mass of an object, or the time. So in other words, as we come back to this table, besides asking, what is its length and its width and its height of this table, we might be asking how many atoms are in, I shouldn't say how many, but the mass, the mass of this thing. And that would be a physical quantity. Time, we might ask how much time has it sat here, or how much time before class ends. But these are your basic quantities that, moving on out of this chapter, I will just point out that it is these three, distance, mass, and time, that I'm going to call the fundamental ideas that I think you've already been exposed to. And now we're going to start combining those together. And you've already seen me do it a little bit. I've combined distance twice to get area and distance 3 times to get volume. Now we can do things like a rate. We can go a distance in a matter of time. We can say a density, a mass in a particular volume. And we can build these together. And what I want to emphasize then in this first chapter, as I kind of wrap this up here, is everything we do this semester is made of these three. It's a mass, it's time, it's a distance. And we'll start doing some pretty complicated stuff before the semester is over. But those are our combinations of pieces that we're going to put together. And as I said, the first thing we're going to do is rate of distance, and we'll call that velocity. And then we'll say the rate at which velocity changes, so we'll call that acceleration. Then we'll say how much push do you have to get that acceleration, so we'll call that force. And the force over distance, and we'll call that energy. Then we'll have momentum. And the list goes on as we build these different ideas together. But keep this pattern in mind. This is going to be our thinking process, that we're going to ask a new question. And a new question comes with a new quantity, which comes with a new symbol. And then we'll get a new formula, and then that formula will give us the appropriate units for that, at which point we will kind of examine the meaning of those units so we can understand the quantity of, say, force or energy. That's the big picture I wanted you to see. And so I should probably put here the symbols that we like to use for mass and for time. And so if you see a lowercase m, that's for mass, and a lowercase t, that's for time. I should emphasize, though, careful with this lowercase m, because didn't we see it for the meter? And we also saw it for the milli. But those are different categories. So remember I said it's okay to use the same lowercase m again if it's a totally different category. That's why it's so important to understand that this is the category of units, and this is the category of the quantity. And filling out the rest of this table, I should probably then emphasize that in the metric system, the unit of a gram is used to measure mass, and a second is used for time. In fact, the metric system and the English system still use the second. The metric system never converted over to a base 10. In fact, when I worked years ago at Boeing, we had a time clock that there was an attempt to kind of turn time into a metric standard and a decimal. And so every hour had 100 minutes. And that it confused us. It didn't make things better. It made it worse. And we just said, forget this. Somebody would say, meet at 2.5, and it was like 2.5. Okay, do you mean like 2:30? Yeah, so 2:30. Okay, so why don't you say that? Anyways, it didn't work well. Anyway, that's a funny life story there. But anyways, that's the idea of the units are just the same for metric system as for the English. It's still a second. And so like I was saying, I'm just going to combine those together. So again, to wrap this up, let me just do this. Let me just ask a couple of questions here. What if I were to tell you the radius of the Earth? Now, the Earth's not a perfect sphere, but let's think of it for a moment as a perfect sphere, and let me just give you the radius. So I'll say radius of the Earth, I'll put a capital R here, is 6.3 how many decimals should I use? Yeah, I'll do 3. 6.37 million meters. So there's the radius. Okay. My first one would be, what if I wanted to know how many miles that is? Could I convert it? Now this is a good one and a long one. 6.37 million meters. So I'll start there. That's the known one. I want to multiply it by 1. Now, I suppose one option is to go Google or look in my book and say, well, how many miles are in a meter? Okay. And maybe that's the approach I'll take. But I want to point out then that I would put meters in the bottom and I'd put miles on the top. That was the first thing I was trying to show you before our break. Okay. Is think about where you are, where you want to go. So the idea of getting rid of it, the one you have you put downstairs, where you want to go you put upstairs. Now, it has to equal to 1, otherwise you would be changing it when you multiplied it 1. So you have to put upstairs the same as downstairs. Now, I know that 1 mile is 1,609 meters. Okay. Now that looks really good, because then I can start off and say, well, I've already messed with my units, so this is going to tell me how many miles. This is the radius of the Earth, okay. And I'll get out my calculator. 6.37 million times 1 divided by 1,609, and I get 3,958.980733 miles. Of course, I have a huge problem. I hope you see it. What's wrong with that?
Sig figs.
Right. Sig figs, meaning that, hey, wait a minute, how could my answer have more meaning and more value, more significant figures than what I started with, my data? In fact, it can't. That was our whole point a moment ago, that you can't have any more significant figures in your answer when you're multiplying and dividing, and that's what I'm doing, than what you have in your data that goes into it. All right, so my answer needs to be emphasized that I really don't know these numbers. But my calculator gave it to me. But I'll say it again, remember, your calculator gave it to you because your calculator is treating everything after this as a 0, everything after this is a 0, everything after this is a 0. And is that really what they are? No. Those are math numbers. That's what your calculator would say. So how many significant figures then should be in my answer? Well, let's start here. How many significant figures do I have here? 3. What about this?
Those are all zeros.
Yeah, okay, so that's what you would call just the placeholder, really. That's really telling me how big the number is. So this is really meaning 6.37, I don't know, I don't know, I don't know, I don't know, right? Okay, so 3, agreed. How about this one? How many significant figures are here? 4? How many are here?
Well, considering it's a ratio, isn't the total sig figs 4?
And why do you say 4?
Because it would be 1 over 1609, which to a decimal would be 4 sig figs, right?
You're on the right path. But so I'll say yes to that. But here's what I wanted you to say is, when I came over here and wrote 1 mile is equal to 1,609 meters. Here's what I really meant. Okay, these are not math numbers. I meant this. I meant 1 mile exactly How many significant figures are there?
Unlimited.
Infinite. And this is why I want to make sure I did this one. This can be confusing. When you have a number, a solid number, I mean, this is not a science number. This is a math number. This is the number 1.00 forever. So you ever come across something like that, there's an infinite number of significant figures. Because it literally means 1 point forever.
And then that's the case for the 1609 as well.
Okay, now, no, not exactly. No, so the 1609, and then there is another number. I just don't know what it was. I mean, I could go over here and probably Google it and get a better answer. But what I'm saying is exactly 1 mile. So one of these two is an exact number. 1 mile is exactly 1,609 and then a little bit more. And so this is the side that has the unknown in it. But I know 4 of them. So I would say this side has 4. This side has an infinite. And this factor has 3. So I would be limited to 3 would be my answer. All right. So all of these are inappropriate. And I guess then that would give me 390. And that one would still be an unknown, but it's closer to the 6. And this also is very confusing. How many significant figures are there? Yeah, and really we like to say 3 because this 0, I would say, is actually just telling me how big the number is. It's not telling me that I actually know the number. In fact, it's why we have this thing called scientific notation, because with scientific notation, you can clearly know how many decimals are significant, and then the multiplication factor is telling you the size of the number. And so the neat thing about scientific notation is everything you write is a significant figure. There's never a doubt. But zeros can be confusing. Because did you notice I counted the 0 here? How come?
Because it's not indicating how big it is.
Right, it's something I really know. It's not, it's not quite 10, it's only 9. That's a known number. And so in that case, it's treating it as a number, not as something indicating how big the number is. The simple answer is if you ever see a 0 between 2 other numbers, you know it's not holding how big the number is. It's actually just telling you a valuable number, that it's 0, not a 1, or not a 2, or not a 3. So the general rule, we like to say, if you ever see a 0 between 2 other digits, it's significant. You wouldn't have put it there otherwise.
If it's 2 zeros in between 2 numbers,
Still works.
still works.
Yeah, because if you start writing a number on this end of it, you mean you measured it to that small, and everything bigger than that you must have measured too. Yeah. Like I said, this one sadly can get confusing. A lot of times there'll be a mark made as an indication how many of these are significant figures. So if I put a line under there, that would tell me 3. But if I put a line under this one, that would tell me 4. Another giveaway is if I put 0.0, there's no reason for me to write that 0.0 as indicate how big the number is. That must be a significant one. And since this 0 is between them, then it must be a significant one. And again, I should probably just say I'm probably focusing too much on this because this is, again, what our chemistry program does.
Miles.
Oh, yeah, and thank you, Ryan. And then let me not forget, since I'm focusing so much on significant figures, units, and without units, it doesn't mean much. Because obviously there's a difference between a mile and a meter. All right, you get the idea. And maybe I'll just do one more and wrap it up here and say, okay, well, what if I asked you this? What is the surface area of the Earth? Now, I partly like this one is because it's going to make you think a little bit and really go back into your previous education. And in this case, I guess I would say somewhere, maybe geometry, you learned how to calculate the surface area of the sphere. Anybody remember it? But even those words, the surface area of the sphere, did you see I also went back and I said, I'm thinking in my mind of the Earth as a globe, right? As a sphere. And so the first thing I had to do was to say, okay, wait. What is the geometric shape of the Earth? Before I can take this next step and say, okay, now what is the formula for calculating the area of a sphere? And I think for you guys in person as well as you guys online, I think that's going to be your challenge, right? It's like, wait. I know I did this math somewhere. Shoot, it was probably 9th grade, but somewhere. I remember talking about a sphere. Now, fortunately, you can look it up and say, okay, I can go look that up. But here in class, I'll tell you, I remember it. It looks like nobody remembered it, but it is 4 pi r squared. And if I did volume, it's 4/3 pi r cubed. So there's the surface area, and there's the volume of a sphere for any of you who wanted a little review here. Okay, so now watch this. I'm going to put in the 4 pi, and then I'm going to jump over here to what was given. The area was given, 6.37. So 6.37 times 10 to the 6th meters, and then I'll square it. And this will give me a great opportunity to say, treat your numbers and your units the same way. Now maybe I need to remind you, somewhere, probably middle school, you learned about exponents. XY quantity squared would be what? X squared, y squared. And so what this would mean right here is I would square not only the number, but also the unit. And so when I'm done here, I would have the area of the Earth in square meters. Perfect, because isn't that what we said must be the appropriate unit? Oh, let me give you a helpful hint. We call this unit analysis. If you are starting a problem, then you read the problem. And like I said, this is going to be your challenge. You're going to read the problem. You're going to follow through on the problem. You're going to take your thinking process, and you're going to try to change that into equations. And that's tough. Okay? And so you'll be a little weak at it at first. That's fine. But that's my job here, right? I'll try to get you to take your thinking process and change it into an equation. All right. So you change it into an equation. Now you logically go through that equation. You come up with an answer. If the units you get at the end do not match the quantity you're calculating, you made a mistake. See, if I came up with anything other than square meters, I know something in my thinking process went wrong because I'm asked to find area, and if I don't come up with square meters, then I'm not using the right units to measure area. And so we call that a unit analysis, and it's a very powerful tool. It'll stop you right in the tracks and go, ooh, clearly I did something wrong. I mean, it asked for the area of the Earth, and when I got done, I have cubic meters. Well, that doesn't make any sense. Cubic meters is a volume. It is not an area. I must have done something wrong. And so unit analysis, very, very powerful tool. So I'm going to keep saying it. Follow your units. Do the same mathematics with your units as your numbers. Don't just blow them off until the end, because it will catch your mistakes. Now, I must admit, if you got your units right, it doesn't necessarily mean you got the number right. So it's not a guarantee you did it right, but it is a guarantee when you did it wrong. It'll show you when you got it wrong. All right, so now let's run through the numbers here. All right, so I've done my units. Let's grab my calculator and let's do the numbers. And so I'm going to take a 4 and hit a times. Oh, then pi, and I'm just going to use the little pi key on my calculator. Hit times, okay. Then I will put in the radius, 6.37 times 10 to the 6th, and I will then hit the square button. So again, remember, I'm squaring both of these. It's kind of the comment I made earlier, making sure I square the numbers. Okay, so now I hit enter, and I get 5.0990436 times 10 to the 14. And of course, I purposely made a big mistake here. What's my mistake?
So when it's 4 pi, that's 4 times the infinite number, so that's infinite sig.
And that's what I'm getting at, is how many sig figs should I have? Let's start with the first number, 4. How many significant figures are here? Infinite. Right? This was not a 4 and I don't know. This was not a measurement where I say, how long is it? Oh, it's 4 meters and something else. This is not a 4 point I don't know. No, this is a math formula, which I guess you kind of have to go back to where they derived this, but it means exactly 4. It wasn't 4 and I don't know. It was 4.0000000. So I would say that this first number has an infinite amount.
Are most like given quantities have infinite like significant figures?
Yeah, because it's a measured quantity that would then have something that we didn't measure it more accurate than that. Yeah. But I want to be careful with that phrase, given, because given could be, I give you a measurement, you know.
You find in the equation.
Yeah. But usually when you have something, it does beg the question, you know, did they really mean exactly 1? Or did they mean exactly 1,609 meters equals something close to a mile? You know, so which did they mean? So it does run into some confusion. Okay.
Room 130?
Is this 130?
Yeah.
Yeah.
For physics?
You're a little early. You're for physics 102 at 11?
102, yeah.
Yeah, hang on.
All right.
We'll be done soon.
All right,
Sure. So this is an infinite number. How many are in the pi? Well, I wouldn't say infinite, because I hit the pi key, and if you look at that, it gives me pi 3.141592654. It gives me 10 digits. There's more. But that's not what the calculator gave me. So I would say that one depends on how you entered it. And since I used the pi key, I'd say there's 10. If you entered 3.141592, then how many did I say? 7. Right? And so however far you've memorized pi. If you only got pi memorized to 3.14 and you hit 3.14, well, then you only have 3. So this is a call on your part. I would just say use the pi key on your calculator, and that's 10. And that way, pi is not limiting your answer. It's something else that's going to limit your answer. Okay. All right, so I've got 10 here. And then, of course, we've already talked about this one. There's 3. So that's the smallest one, 3. And it's actually multiplied twice. So it's 3 and then 3 again. But the bottom line is the smallest is 3. My answer should have 3. And so 3 would come out to be right here. So this would be 5.10 times 10 to the 14th. And again, you can see the 0 would be counting as a significant one because it is, well, it's in scientific notation, but it's also not needed to tell me how big the number is. And so I would say I have the surface area is 5.10 times 10 to the 14th. We could, I guess, even do a little metric here. 510 tera square meters. Because tera would be 10 to the 12th for trillion, and then times 2 would go here. And so I can do a nice unit conversion there. Maybe a little too quick.
Do you want us to do unit conversions like that?
Oh, no, I would be very happy with that. Right. Usually, and just because big numbers are kind of hard to say, people like this. 510 trillion square meters is a lot easier to say, I think. And 1.5 times 10 to the 14th meters squared. 10 to 14th, what is it? Anyway, So that's why we have these prefixes, so we can always just have a small number in front and then have tera or mega or micro or femto or nano or something. Okay, well, I better keep going here. I'm going to wrap this up here. Here's, I think, a better question. Now that I got this answer, so let me just write it down. 5.10 times 10 to the 14th square meters. How many square miles is this?
That times 1609
Very close.
meters.
You square your 1609.
Good. Okay, watch. Let's talk this out. And let's say it all again. What do I have? Where do I want to go? So I have square meters, not meters. I have square meters. And I want to get square miles. Now, that makes me think that I should put meters on the bottom, miles on the top, and as you said, then if I'm multiplying by 1, I would put a 1 mile here and 1,609 here, but do you see a problem with this if I stopped? The problem is I have square meters, but I don't have square meters down here. So this would not get rid of it.
So you'd have to square that.
And fortunately, 1 squared is still 1. And if you want to take an intermediate step, then I could say, well, that'd be 1 squared. That would be a mile squared. That would be a 1609 squared. And that would be a meter squared. And that's exactly what I need in order to cancel off the square meters to give me 8 square miles. And do you see how I'm still multiplying by 1? And you see, no one needed to tell you to square it. Right? Figure that out. You knew it didn't fit. It didn't match. The units didn't work out. The unit analysis, it was not going to come out right. There had to be something more to that. So I had to change it. And when I say change it, I had to multiply by 1. I couldn't multiply by anything that would actually physically change it. I had to be something that would multiply by a 1. All right. So now I can get my calculator, now that the units work out right, and say, all right, let's put this into my calculator. 5.10 times 10 to the 14th times 1 squared. Let me not even just put that in my calculator. That's just a 1. Okay. Then divided by 1,609 squared, and I get 1.96996 times 10 to the 1, 2, 3, 4, 5, 6, 7. And of course, same as before, what about our significant figures? Well, this has 3. This is that exactly 1 mile, so this has an infinite number. This has 4, because then it's, point something. I just don't know what that is. And I done it twice, so there's a 4 again. So 4, 4, infinite, 3. The smallest is 3, so I should have 3, and so that would 1.97, because these other ones would be I don't know, times 10 to the 7th miles squared. So there's the surface area. Well, I didn't give us a chance to actually get started in chapter 2. Bummer. So I'm a little behind already, but I hope this was helpful. Maybe I'll just call it 5 minutes early and say, why don't we take a 15-minute break before we regroup here for the lab? And so I'll say bye to you guys online and say we'll pick this up tomorrow with chapter 2 and actually get started with physics now that we know a little bit about science and numbers and calculations and converting units. Bye now.